Most people think light is simple. You flip a switch, the room glows. The sun rises, the sky turns blue. It feels harmless, ordinary, almost boring. But that's because we've trained ourselves to ignore the strange part. Light is not just something that moves through space. According to Albert Einstein, space itself is not a rigid stage where events happen. It stretches, it bends, it evolves. And once you accept that, something deeply unsettling begins to emerge. Imagine you throw a ball across a room. If the room expands while the ball is flying, the ball doesn't slow down just because the walls move. But light is not a ball. Light is a wave, and waves care about the size of the space they occupy. Now here's the strange part. When the universe expands, light doesn't resist. It stretches with space. Its wavelength becomes longer. And when wavelength increases, energy decreases. That's not philosophy, that's physics. So every photon traveling across the cosmos is slowly losing energy simply because the universe is growing. Pause there. No friction, no collision, no energy transfer in the usual sense. Just expansion. If you look through powerful telescopes like the Hubble Space Telescope, you see galaxies billions of light years away. Their light is redshifted, shifted toward longer wavelengths. The farther away the galaxy, the more stretched its light. That stretching isn't cosmetic, it's a loss of energy. Now, a curious mind should immediately ask, where does the energy go? In everyday life, energy conservation feels absolute. You drop something, it converts potential energy to motion. You burn fuel, chemical energy becomes heat. Energy changes form, but it doesn't vanish. But on cosmic scales, things are not so tidy. In an expanding universe, global energy conservation isn't as straightforward as in a closed box. There is no cosmic ledger that balances the total energy of every photon across expanding space-time. The equations of general relativity allow space itself to evolve, and that evolution changes the energy of light. That means trillions upon trillions of photons, traveling for billions of years, are gradually being diluted. Their energy thins out as space stretches. Now imagine this happening everywhere. The universe isn't just filled with matter. It's flooded with radiation. Starlight, relic radiation from the early universe, photons streaming in every direction. And all of it is slowly losing energy to expansion. It's almost poetic. Light races across the cosmos at the fastest speed allowed by nature. Nothing outruns it. Nothing catches it. And yet, over time, the universe quietly drains its strength, not violently, not dramatically, but inevitably. If you step back and look at the big picture, you realize something astonishing. The universe is not a static container filled with light. It is an active participant in reshaping that light. Space is not passive emptiness. It stretches, and in stretching, it transforms radiation itself. So when you look at a distant galaxy, you are not just seeing ancient light. You are seeing light that has been altered by the expansion of reality. You are seeing photons that left their source energetic and sharp, only to arrive stretched, cooled, and weakened at fact. Light doesn't just travel through the universe. It evolves with it. And once you see that, the universe stops looking empty and starts looking alive with quiet, relentless transformation. Take a beam of light leaving a distant galaxy, not a metaphorical beam, an actual photon born in the heart of a star, blasted outward by nuclear fusion. It begins its journey energetic, sharp, vibrating at a high frequency. If you could see it at the moment of departure, it would carry a precise amount of energy, like a perfectly tuned musical note. Now let it travel for 1 billion years. Then another billion. By the time that light reaches our instruments, like the Hubble Space Telescope, it is no longer the same note. its wavelength has stretched, its frequency has dropped, its energy is lower. This is what we call redshift. You can think of it like drawing waves on a rubber band. If you stretch the band, the waves get longer. Nothing mysterious about that. But here's the twist. In the universe, the rubber band is space itself. According to Edwin Hubble, distant galaxies are receding from us. The farther away they are, the faster they move. That observation changed cosmology forever. It told us the universe is expanding. But expansion doesn't just move galaxies apart. It stretches the very fabric through which light travels. And when light stretches, its energy decreases. Now here's where the simple story becomes unsettling. Energy, we're taught, is conserved. It doesn't disappear. It transforms. That principle feels sacred in physics. You burn wood, you get heat. You compress a spring, you store energy. The bookkeeping always balances. But when photons redshift due to cosmic expansion, their energy decreases, and there's no obvious place it goes. It's not converted into heat. It's not absorbed by anything. It doesn't pile up somewhere else. It simply becomes less. If that sounds uncomfortable, good. It should. Because the conservation of energy that works beautifully in laboratories becomes subtle on cosmic scales. In the framework of general relativity, energy conservation is local, not necessarily global. In a dynamic, expanding space-time, there isn't a universal energy meter keeping track of everything. So imagine the implication. Every second, stars across billions of galaxies emit unimaginable amounts of radiation. Over cosmic distances, that radiation is stretched. Over cosmic time, it loses energy. Multiply that by trillions upon trillions of photons. The universe is filled with this quiet energy dilution. It's like an enormous reservoir, slowly leaking, not because of cracks, not because of theft, but because the container itself is expanding. And here's the fascinating part. The redshift is not random. It increases with distance. The farther the photon travels, the more it stretches. That means the older the light, the more energy it has lost. When we look at extremely distant galaxies, we're not just seeing them as they were long ago. We're seeing light that has been weakened by the growth of the universe itself. So the cosmos isn't just expanding spatially, it's reshaping the energy of radiation within it. And once you see that, a strange question forms naturally. If the universe is constantly reducing the usable energy carried by light, what does that mean for its long-term evolution? The redshift isn't just a measurement tool for astronomers. It's a sign that the universe is dynamically altering the very radiation that fills it. Light leaves its source powerful and energetic. The universe ensures it never arrives the same. In the late 1990s, astronomers were not trying to rewrite the universe. They were doing something beautifully ordinary, measuring explosions. Specifically, distant stellar explosions known as Type Ia supernovae. These are useful because they shine with nearly the same intrinsic brightness, like standard cosmic light bulbs. Measure how bright they appear, and you can estimate how far away they are. Two independent teams, including the Supernova Cosmology Project, looked at these explosions across vast distances. They expected to see a universe slowing down. After all, gravity pulls things together. If the universe began in a hot, dense state, the aftermath of the Big Bang, then gravity should have been tugging on galaxies for billions of years, gradually reducing the expansion rate. That's what intuition said. That's what most cosmologists expected. But the data refused to cooperate. The distant supernovae were dimmer than predicted. Not just a little dimmer, systematically dimmer. The simplest explanation was shocking. The universe was not slowing down. It was accelerating down. Now think about what that means. Acceleration requires a cause. If galaxies are moving apart past haste, reft, Earth. Something must be driving that acceleration. Gravity can't do it. Gravity attracts. So cosmologists introduced a new ingredient, something that acts like repulsive gravity on cosmic scales. They called it dark energy. It's a humble name for a colossal mystery. Dark energy is estimated to make up roughly 70% of the total energy content of the total energy content of the universe. Not atoms, not stars, not dark matter, something else, something invisible, something that pushes space apart. But here's where the Feynman-style curiosity kicks in. When you invent a new term in physics, it's often a placeholder for ignorance. Dark energy doesn't explain the mechanism. It labels the observation. We see acceleration. We need a cause. We give it a name. Now, one popular interpretation is that dark energy is a property of empty space itself, what Albert Einstein once called the cosmological constant. In the equations of general relativity, you can add a constant energy density inherent to space. As space expands, more space appears, and with it more of this energy. The effect is a self-sustaining acceleration, but that raises uncomfortable questions. Why does this energy have the value it does? Why is it so small compared to predictions from quantum theory, yet large enough to dominate cosmic expansion today? Whenever physics produces a number that seems absurdly fine-tuned, alarm bells ring. And that's where deeper thinking begins. Could our interpretation of cosmic acceleration be incomplete? When we observe distant supernovae, we rely on light. Light that has traveled billions of years. Light that has been stretched, redshifted, and diluted by expansion. All our conclusions about acceleration come from how that light behaves. So the puzzle becomes subtle. Are we seeing pure geometric acceleration, or are we interpreting complex radiation behavior within expanding space-time? This doesn't mean dark energy is wrong. The evidence is strong. Multiple observations, supernovae, cosmic background radiation, galaxy clustering, point toward acceleration. But the conceptual shock remains. 70% of the universe is something we do not understand. And whenever physics reaches that point, history suggests one of two outcomes. Either we've discovered a profound new component of reality, or we're missing a deeper principle hiding in plain sight. That tension between confident measurement and incomplete understanding is what makes modern cosmology so thrilling. We measured exploding stars and ended up confronting the possibility that most of the universe is powered by an unknown force. If you want to see the universe as it once was, you don't need a time machine. You just need to look far enough away, because light takes time to travel. Every distant observation is a glimpse into the past. And if you look far enough, not millions, not billions, but nearly 14 billion years back, you encounter a faint glow filling all of space. That glow is what we call the cosmic microwave background. It is the afterglow of the Big Bang, not the explosion itself, but the moment when the universe cooled enough for light to travel freely. Before that time, the cosmos was an opaque plasma, a dense fog of charged particles scattering photons endlessly. Light couldn't move in straight lines. It was trapped. Then, about 380,000 years after the beginning, something profound happened. The universe cooled. Electrons combined with protons to form neutral atoms. Suddenly, photons were no longer constantly scattered. Space became transparent, and the light that escaped at that moment is still traveling today. But it hasn't remained the same. Originally, that radiation was not microwaves. It was blazing hot, thousands of degrees, glowing like the surface of a star. If your eyes had been there, you would have seen a brilliant white-hot universe in every direction. Now measure it today. That same radiation has a temperature of about 2.7 degrees above absolute zero, barely detectable without sensitive instruments like those aboard the Planck spacecraft. What was once a searing flood of energy has been stretched into faint microwaves. What happened was just space expanded. And as space expanded, every wavelength of that ancient radiation stretched with it. The peaks of the waves moved farther apart. The frequency dropped. And because energy and light depends on frequency, the energy dropped too. This wasn't a small adjustment. It was a transformation across billions of years. Imagine taking a bright white flame and slowly turning it down until it becomes a faint whisper of warmth. That's what cosmic expansion has done to the oldest light in existence. Now here's the thought that should make you pause. The cosmic microwave background isn't a local phenomenon. It fills all of space. Everywhere you point a detector, you find it. That means the entire universe is permeated by radiation that has been steadily losing energy for nearly its entire history. It's like the cosmos is carrying a fossil record, not in rocks, but in light. And this light is cooling, not because it radiates into something else, not because it's being absorbed by a giant cosmic sponge. It cools because the fabric of space itself stretches. The universe doesn't just expand outward into emptiness. It expands internally. The distances between points grow. And in that growth, radiation is diluted. If you think about energy in a fixed box, it feels stable. But if the box itself grows larger and larger, the same energy spreads thinner and thinner. That's what's happening on a cosmic scale. So when you measure that faint microwave glow, you are not J. Used detecting ancient photons. You are witnessing the long-term effect of expansion on radiation. The early universe was dominated by radiation. Today, that radiation is a whisper. And the only reason it faded is because space itself grew quietly, relentlessly, reshaping the energy of the cosmos without ever touching it. There is a simple law in physics that feels almost philosophical. The second law of thermodynamics. It says that in an isolated system, entropy, a measure of disorder, tends to increase. Things spread out, energy disperses, structure softens into uniformity. It's not a dramatic law. It doesn't shout. It doesn't explode. It just quietly insists that over time, differences fade. Now place that idea on a cosmic scale. Imagine the early universe, hot, dense, filled with intense radiation. Energy packed tightly together, photons colliding constantly. Matter and light intertwined in a brilliant plasma. It was structured in its own violent way, but it was concentrated. Then expansion begins to stretch everything. Radiation spreads out. Wavelengths lengthen. Temperatures drop. The once blazing glow that later became the cosmic microwave background cools from thousands of degrees to just a few degrees above absolute zero. That cooling isn't random. It's entropy in action. When light expands into a larger volume of space, its energy density decreases. The same number of photons occupy a greater and greater volume. They become more dilute, more uniform, less capable of doing useful work. And that phrase, useful work, is crucial in thermodynamics. Not all energy is equal. Energy concentrated in gradients, hot next to cold, dense next to empty, can power change. At once everything evens out. Once temperatures equalize and motion becomes uniform, you can't extract anything meaningful from it. That final state has a name, heat death. It does not mean an explosion. It doesn't mean collapse. It means stillness. A universe where stars burn out, galaxies fade, and the remaining photons are stretched so extremely by expansion that their wavelengths become enormous, perhaps light years long. Their energy approaches zero. This picture emerges naturally from the combination of thermodynamics and cosmic expansion described by Albert Einstein in general relativity. As space expands, radiation thins. As radiation thins, entropy increases. Now here's the striking part. Expansion doesn't destroy photons. It doesn't annihilate them. It stretches them. And in stretching them, it reduces their ability to influence anything. Over unimaginable timescales, light becomes so diluted that it can barely interact with matter at all. It's a slow fading. Picture a drop of ink in water. At first it's dark and distinct. Over time it diffuses until the entire glass has a faint tint. Eventually the difference becomes almost imperceptible. The ink is still there, just spread so evenly that no structure remains. That's entropy. And the universe is performing this experiment with light itself. If cosmic expansion continues, and especially if acceleration driven by dark energy persists, this dilution speeds up. Galaxies move beyond each other's observable horizons. Starlight redshifts into invisibility. Even the cosmic background radiation stretches further into silence. In that far future, observers, if any exist, would see a dark, cold sky with almost no information about the fiery origin of the cosmos. So when we say the universe is eating usable energy, we don't mean it in a violent sense. We mean that expansion spreads energy thinner and thinner, increasing entropy and reducing structure. Light begins as brilliance. Given enough time, it becomes a whisper. And thermodynamics guarantees that the whisper is the call. Direction the universe prefers. There's a habit we have when we think about light. We treat it like a traveler. It leaves a star, crosses empty space, arrives at our telescope. A messenger, a passive courier carrying information from one place to another. But that picture is incomplete. In the equations of general relativity, light is not just something moving through space-time. It contributes to space-time. Energy and momentum, including that carried by radiation, affect curvature. Curvature affects motion. It's a feedback loop. In the very early universe, radiation wasn't a minor detail. It dominated everything. The energy density of light was higher than that of matter. Photons weren't background decoration. They were major players in cosmic dynamics. If you could travel back to those first tens of thousands of years after the Big Bang, you wouldn't see galaxies or stars. You'd see a seething ocean of radiation controlling the expansion rate itself. The equations show it clearly. When radiation dominates, the universe expands differently than when matter dominates. So light has already shaped cosmic history once. Now fast forward. As expansion continues, radiation energy density drops faster than matter density because of redshift, the stretching of wavelengths. Eventually, matter takes over gravitational influence. Later still, something else appears to dominate, dark energy. But here's the subtle question that should make you lean forward. If radiation once governed expansion, and if radiation energy is continuously modified by expansion, are these two phenomena completely separate, or are they intertwined aspects of one deeper structure? When photons redshift, their energy decreases. That changes the energy content of the universe over time. In a static universe, energy conservation feels clean and global. But in a dynamic space-time, the rules are M, or subtle. There isn't a universal master clock enforcing a simple energy ledger across the entire cosmos. And that means expansion and radiation are not independent stories. They are mathematically entangled. Light follows the curvature of space-time. Space-time evolves according to its energy content, and radiation is part of that content. It's a loop. Now, this doesn't mean light is secretly causing today's accelerated expansion. Observations strongly support the presence of something like dark energy. But conceptually, it's important to recognize that radiation is not an innocent bystander. It has massless energy. It gravitates. It influences geometry. In fact, even a box filled with pure light would weigh more than an empty box. Radiation has gravitational effects. That realization alone is astonishing. Something with no rest mass still shapes gravity. So when we imagine the universe expanding and light merely going along for the ride, we're simplifying too much. The ride itself depends on the passengers. In the early universe, radiation dictated the tempo. Later, matter changed the rhythm. Now dark energy appears to conduct the orchestra. But throughout all of this, light has been both messenger and participant. It carries information across billions of years, allowing us to reconstruct cosmic history. And at the same time, through its energy, it has influenced that very history. That's the deeper elegance. Light doesn't just reveal the universe. It helps write the script